Okay, Luke, let's consider our universe somewhat differently to the one we live in. What would our universe be like if we didn't have any quantum mechanics?
Well, I guess we have to say what the universe is like with quantum mechanics first. So this is a topic that, as when you do your training as a physicist, there's a lot of quantum mechanics in there because it's such an important topic. Some of the particularly odd things about quantum mechanics is that we're used to the classical world. We're used to a world with sort of waves at the beach and billiard tables that bounce around, billiard balls, that bounce around billiard tables. But the rules of matter and energy seem to change on very small scales. And even that's a bit of a hairy question of how small. We'll get back to that. But there are these quantum rules about how the universe behaves, and it's very, very unusual, very different to the universe we're familiar with.
So just to get this right in my head, and for our many viewers out there, when we talk about the classical world, the world around us here, we talk about things like Newton's equations, forces, and that kind of thing. And so there's a certain set of mathematics. But then when I want to talk about how an electron behaves in an atom, I now have to use a different set of mathematics. Is this what we mean?
Particularly, it's not just different equations. It's a different mathematical object that represents the system. So if I want to describe where, say, a particle is in Newton's system, all I have to tell you is where it is. And I'll give you a single set of numbers, say X, Y, and Z, right? With quantum mechanics, it's not just that there's a different thing that tells us how it was going to move in X, Y, and Z. The thing that represents, say, an electron is called a wave function. And it's something that is intrinsically spread out over space and time. Now, when we get down to practical experimental details, the wave function tells us where the electron probably is and where it's probably going. So it's a probabilistic thing. But the big question is now, what's going on fundamentally behind the scenes that this wave function is representing?
Okay.
And so what you do with a quantum system is you say you have a certain setup, but when you describe what's going on, you do it in terms of wave functions. In the old school, what's called the Copenhagen interpretation of quantum mechanics that we sort of learned but is now sort of going out of favor, what you said was whenever there's a measurement, then the wave function, which is a set of like the electron's probably here and possibly over here and maybe over here, when you do a measurement, the system will collapse into one of those definitive states. There's a way of saying the electron is definitely here. It will collapse into one of those and then start spreading out again. And the problem with that is, and this is a huge problem, is that it doesn't make a whole lot of sense to say that there's these two sort of sets of rules. Like, when does measurement really happen?
Yes.
As opposed to just the rest of it. But that's a massive problem. But we want to ask a sort of deeper question about what if the universe didn't obey quantum mechanical laws. So, for example, question for you. What if the universe didn't have these different laws at the bottom? What if it was classical all the way down?
Okay, so this is something I remember reading a lot about a while ago. So if it was classical mechanics all the way down to the scales of atoms, etc. So number one is we run into a problem straight away, right? We know that atoms are made of a nucleus, which has positive charge, has protons and neutrons, and we have electrons sort of whizzing around. And that's the classical picture is that the electron is sort of orbiting the nucleus. Now, the problem is that our nucleus and our electron, they attract each other using the electromagnetic force. And we have an entire field of classical electromagnetism. We know how to talk about charges moving in terms of electric fields and magnetic fields. But one of the things that you find automatically is that if you accelerate a charge, it radiates. Now, this is how you make radio waves. You take electrons and you have them in an antenna, you wobble them back and forth, and they radiate radio waves.
Yeah.
Right? That's how you generate any kinds of electromagnetic radiation. You must oscillate charges. If you take an electron in an atom and it's orbiting, it's accelerating. In the same way as the Earth is accelerating towards the sun due to gravity, the electron is accelerating towards the nucleus due to electromagnetism, even though it's tracing out a circular path. And that means that that electron will radiate away its energy as electromagnetic radiation. So if you could even set it up as a stable system, a nucleus and an electron in an orbit, the electron would rapidly lose its energy and it would spin down and basically crash into the nucleus.
Right.
Matter is not stable at the small scale if you don't have quantum mechanics. Right. So that's already pretty bad. You don't get atoms. Right. You don't get atoms at all because electrons would just fall into the nucleus. Let's assume that we can do away with this problem, right? So let's assume that we don't have to worry about the fact that electrons radiate. We can take a nucleus and we can put an electron in motion around that nucleus. Now, one of the things that quantum mechanics says to you is that the orbits of the electron around a nucleus are quantized, right? Which means that there are only certain orbits which are allowed. So I can have my electron orbiting here, I can have my electron orbiting here. But rules of quantum mechanics say you must be in this, or this. Now, that's very important for another minor area of science known as chemistry.
Yeah,
right.
There's a building around here somewhere.
It is around here. It's rather ugly, but but essentially, right. What we're saying is that one thing we know is that if I have a carbon nucleus and electrons, and I have another carbon nucleus and its electrons, and they're in the same energy state, they're going to be identical. The structures of where the electrons are going to be exactly the same between them, right? And it's the arrangement of the electrons on the outer side of the atom that allows that carbon atom to bind with other carbon atoms and other atoms to build molecules. Now, if I had a classical atom where the electrons can orbit anywhere, right? The radius of their orbit could be whatever, the velocities that they move could be whatever. Then that means that this carbon atom and that carbon atom could have different structures in the electrons. The electrons might be doing different things. So then, if I take those two carbon atoms and I start trying to plonk them together to create molecules, then the molecules that I would produce, if you could get things to stick together, would be different, right? Because the way that things stick together depends upon what's going on with the electrons on the outside of the atom. And if your electrons are doing different things, they're going to stick together differently. Now, one of the things that we rely on for life is that our DNA is a very reproducible kind of structure, which is set by the quantum mechanical rules that set where the electrons can go and what they can do. So we even if we had atoms that could survive long term in a classical universe, the molecules that they would produce would be different. They'd be higgledy-piggledy, right? You wouldn't get regularized structure.
Right, so a crucial part of life as we know it, and probably life as we can even imagine it, is this sort of replication, right? It's happening in each of your cells now. Things are being copied.
Yes.
But if you're going to copy something, you have to make the same thing over here as over there.
Yeah.
And it sounds like no quantum mechanics. There's just every molecule is bespoke.
Yes. And it's worse than that, because every atom is bespoke.
Yeah.
Right? Because the nucleus itself is also a quantum system. A nucleus has energy levels, and protons and neutrons sit in those energy levels. And one carbon nucleus in a particular energy state is identical to another carbon nucleus in a particular energy state. But if we just go back to this classical rule where things can be in whatever energy they want to, then this carbon nucleus is different to that carbon nucleus. And so essentially, quantum mechanics on the small scale imposes an order which is then reflected in the fact that we have complexity and structure in the universe, which is kind of interesting, right? But we could play the opposite game.
Yes.
Right? Let's, instead of removing quantum mechanics from the universe of the very small, how about we bring quantum mechanics up to the universe of the very large?
Right. So the world we see around us is the classical world, right? But there's a wonderful set of novels by George Gamow, and what he is called Mr. Tompkins. And he starts sort of playing around in a universe where there's quantum mechanical laws at all scales. And so he starts trying to play billiards, and there are the billiard balls on the table, but they start behaving the way we think electrons behave. So rather than, like, as we see, the billiard ball is at a particular place at a particular time, after you hit the ball, it kind of spreads out and eventually the table, just instead of looking like discrete balls at particular places, now looks like this mess of all the balls are kind of spread out everywhere. Now, that's a bit of a fanciful picture, of course, but it does underscore the fact that these quantum rules are very different. Later in the book, he's on a safari and gets attacked by a quantum tiger at all sides at once. I think one of the particularly weird things about these sorts of worlds is whenever we do information storage in our universe, whether that's in your brain or in a computer or of any kind of thing, what we need is to put the system in a particular state. That seems to be just absolutely basic, right? If I'm going to write down a number on this board, I need to write some particular number. There needs to be, ink in certain places but not others. If I store something on the hard drive, it needs to be a certain selection of noughts and ones and not the other ones. So it seems like if we were in a quantum mechanical world, say we were in a world where whatever happens to make the classical world, whatever that is, and we'll talk about a few options later, whatever that is happens, either doesn't happen or happens really slowly or something like that, most of the world around us would be in not the classical here or here sort of states, but in this sort of weird smeared out, the all options of the wave function are open.
Yeah.
And so it seems like we wouldn't be able to do basic things like storing information. So there's a lot of effort going on in the world now about something called quantum computing. Maybe we can use these quantum mechanical effects to do some calculations in an interesting way. At the end of that calculation, we have to get back to the classical world. We start with some sort of problem, and then quantum mechanics does whatever weirdness quantum mechanics does. But at the end of that, things need to, in the old language, we would say collapse or return in some way to the classical world that we're familiar with, where we can say the answer is 7 and not the answer is some weird quantum superposition of 7 and 5 and 4 and 1 and all those sorts of things. So that it seems like if there was quantum mechanics all the way up, it'd be a very weird universe where, just as we couldn't get replication if there was no quantum mechanics at the small scale, if you had quantum mechanics all the way up, we couldn't store information in the first place to then replicate it. That's a very weird case. There's also in quantum mechanics something called non-locality. So, for example, just the speed of light is finite. I don't actually need to know what's happening in the sun for the next 5 minutes because it's so far away. Its light takes 8 minutes to get here anyway. I need to worry about the sunlight that's coming in for the next 5 minutes. But other than that, I can sort of contain it. In the quantum mechanical world, you can have this property that anything in the universe could be affected by anything else in the universe, no matter how far away it is. It's one of the most deeply mysterious things about it. So if we had a universe where non-locality, where things sort of being affected by things further away was the rule rather than this sort of weird exception that might happen, but we don't have to take it into account in everyday life, it would be very hard to have a universe which was predictable in any sense. And I don't just mean predictable by physicists in physics papers, but simple things like, predicting what will happen when I try to store some information on my hard drive, or predicting what will happen when a cell in my body tries to divide and make a new cell, or a bird trying to catch an insect in mid-flight, or something like that. Just that basic level of what do I think is going to happen next might break down. So we need classical physics there at some stage, and we kind of have in quantum mechanics things where we need them. Quantum mechanics makes the small stuff stable, but it doesn't make a totally weird universe at large scale.
Yeah, so we're lucky that we're in a universe whereby we have quantum mechanics at the small scale, classical mechanics at the large scale. Mm-hmm. But where's the boundary? Where is the boundary? I mean, and what sets that boundary?
Yeah. So there's a very famous thought experiment, which there's so many bad versions of that you worry about.
Should we do another bad version?
Here's another bad version. We might try and sort of get this right. I have read the original paper, Schrodinger's cat. The way this is usually put forward is you put a cat in a box with some device that may or may not kill the cat over the next hour, and it's some sort of weird haiku Buddhist cone or something that, is it sort of alive and dead at the same time? That wasn't Schrodinger's point. Here's his point. He has this sort of diabolical cat-killing device. His point was, what happens if I try to say quantum mechanics small, classical, big, with some line in between? The point of his device was that it crossed over the line. You start off with a radioactive nucleus, which is obviously a small thing, right? We're totally in the quantum mechanical world then. It decays, and it sends out a high energy particle, and we have classical detectors, like a Geiger counter, which can detect that particle. Okay? So if we had to say that the atom itself was some weird quantum superposition of intact versus decayed, we would then have to say that the detector is some weird superposition of I detected it intact or I detected it decayed. Or more specifically, I didn't go off, I did go off. If that detector is then attached to something that breaks a vial which releases poison which kills the cat, we then have to take the weirdness of the quantum smallness and apply it to the cat and say, not just, we don't know which one it is, but we would have to say, if we took quantum mechanics seriously on that level, the cat is in a superposition of the cat is dead and the cat is alive. And what Schrodinger's point was not, isn't that weird? Schrodinger's point was, that's not the universe we see, ever. We only ever see a live cat or a dead cat. So there's something about, we can't just say quantum small, classical big, with some line at a billionth of a meter, and that'll just divide all of that. We have to do something a bit better.
And that better is, and this is where we run up against modern physics, because at some level we don't really know, right? That it's some ideas.
It's a very open question. So part of this goes just simply into how do we interpret quantum mechanics? Like, what is this thing trying to tell us about the world?
Yeah.
One particularly fruitful line of inquiry is an idea called decoherence. So what was noticed was the following. If I take a system and I describe it with quantum mechanics, and I keep track of everything that I started with as it interacts, like, the nucleus decays, the detector goes off, the cat dies, all of that. If I keep a handle on everything, all of the quantum mechanical weirdness is still there. But if I lose track of part of the system, right, the system, say, light rays come in the window, bounce off the cat, and then go back out the window beyond any detector that I've got. It's a something that was discovered in quantum mechanics. Actually, the bit that's left over, you lost some of it. The bit that's left over seems to behave according to classical rules, right? So that's an interesting little clue there, right? If maybe what counts as a measurement, what counts as why the universe looks classical, is because we're only observing part of it. We can't, in practice, keep a track of every little bit of the universe. And so in particular, if you've got something big like a cat, you'll never keep track of every light particle that bounces off the cat. You just look at the cat, you see the individual light particles that bounce off the bit of the cat that you're looking at. Now that doesn't totally answer all our questions, because, right, why do I see, if there were two options, why do I see one and not the other is still, and what determines whether I see one and not the other? And there's an awful lot still going on here, but that seems like an interesting clue.
So one of the things that has interested me recently is this notion of how big something can be, and you can still see quantum effects. So maybe there's no well-defined boundary. As you said, it might be to do with how it interacts with everything else, and if you can keep those interactions away, then maybe the thing behaves quantum mechanically. And there's this question of, when you fire something through a slit, quantum mechanics says you get diffraction. And so how big can you make something that it still behaves like a wave when it goes through a slit? And my understanding is that at the moment you can do molecules with up to 10,000 atoms in them, and they will behave quantum mechanically as they go through the slit. Now, 10,000 atoms is a lot of atoms, but it's not. It's many less atoms than many fewer atoms, many less atoms. You can't count them. Than you have in your body, right? But you get there. What happens when we are able to fire live things through the slit. A virus, right?
Yeah.
Okay, and then a bacteria. And how does that behave quantum mechanically as it goes through? What happens when we can eventually fire a cat through a slit?
Yeah, well,
That's something to think
that's
about.
a very, very open question. The real thing would be, if we could then ask whatever it was that went through the slit, in particular, if you could send something that could record something.
Yeah.
I don't know, it's a simple recording device through. What happens then? That would be very interesting.
But that's a topic that's bigger than this little video here.
Indeed. We'll tackle that another day.
We will.